Thank you to the organizing committee for inviting us to present our paper, Estimating Policy Functions in Payment Systems Using Reinforcement Learning. This is joint work with Pablo Samuel Castro from Google, Ajit Desai and Handu from the Bank of Canada, Rod Garrett from UC Santa Barbara, and me, Francisco Rivadeneyra from the Bank of Canada as well. Standard disclaimer applies. These are opinions only and not the ones from our institutions. What motivated us to look into this problem? Central banks are charged with ensuring the safety and efficiency of high-value payment systems. High-value payment systems are used to settle transactions, payments between financial institutions, mostly banks. And as such, they're part of the national financial infrastructure. Think of it as the electric grid. Banks use these systems to pay on behalf of their clients, and to do so, they first need the liquidity provided by the central bank, which is costly. An incoming payment from another bank is also liquidity that can be used for their own payments, giving an incentive to free ride on others' liquidity. Further, payment requests from the clients and the timing of an incoming payment are uncertain, giving rise to a multi-agent game of incomplete information. Most interestingly, this game can have cooperative and non-cooperative solutions. In other words, the same system can be efficient or inefficient. To aid in achieving the efficiency of these systems, we need to understand the behavior of participants. So this is the objective of this paper. We want to approximate the policy rules of banks participating in these systems using reinforcement learning. You might ask, why use reinforcement learning? What does it bring us? Reinforcement learning is quite suited for this task. Reinforcement learning trains agents to behave optimally in sequential decision tasks, mapping observations, potentially partial, of the environment to complex action choices. One of the key strengths of RL compared to other methods is we can specify a really broad learning environment, can be stochastic, multiple agents. So in the context of payment systems, we're going to have an environment in which the participants will learn to interact in the payment system to learn a policy to choose the amount of liquidity necessary to process their payments. Our key result is that the agents trained with reinforcement learning learn the optimal policy, which minimizes the cost of processing their individual payments.
Thank you, Francisco, for building up the motivation. Hello, everyone. This is Ajit Desai from Bank of Canada. I will quickly overview a high-value payment system environment. Our payment system environment is real-time gross settlement or RTGS system. That means transactions are settled in real time without netting. For example, two offsetting positions between two banks cannot be cancelled out even if they were submitted at the same time and for the same amount. We choose RTGS system because it is typically used by many countries around the world. Consider a simplified RTGS payment system with only two participants, Bank A and Bank B, as schematically shown on the slide. Each bank has its own payments demand, most of which is generated through their client's request, and some of these payments demand might be related to their own activity. In order to exchange these payments, they need liquidity, which can be arranged in two ways. The first, at the beginning of the day, by pledging collateral to the central bank, which then provides liquidity in proportion to the pledged collateral. And the second, throughout the day, they might receive payments from other participants, which they can use to send their own payments. In our setting, we also impose following condition. At the end of the day, each bank has to satisfy their payments demand. If the bank does not have sufficient liquidity, they will borrow from the central bank. Let's go through a typical day in our system. The start of the day procedure is depicted in schematic shown on the right. At start, that is in period 0, a bank has a collateral denoted by B. This bank wants to pledge the part of this collateral to the central bank. In order to get the initial liquidity denoted by L0, and there is a cost associated with this decision denoted by RC. More they pledge to the central bank, less they have to use somewhere else. Therefore, it is also called opportunity cost. The initial liquidity decision denoted as X0, which is discretized between 0 and 1, where 0 means pledge nothing and 1 means pledge everything. This is a key decision that each bank has to make in this system. This is a strategic decision because the timing of arrival of incoming payment depends on how much initial liquidity other bank posts. If the other posts more liquidity, that means incoming payments are likely to arrive sooner. In that case, a bank can send more of its own payments using the received liquidity and thus require less of its own liquidity. Let's see how that unfolds during the intraday. The intraday procedure is outlined in schematic as shown in the right. Let's discretize the day into T intraday period. In each of these periods, agent receives payments demand PT from their clients. Also, in each period, the agent has to make a decision how much to send. It is denoted as XT in first equation. This choice is constrained by the available liquidity in that period. Although this decision could also be strategically chosen, like initial liquidity, however, in this paper we simplify this decision to send as much as possible. If the agents have enough liquidity, they send all. Otherwise, they send equal to the amount which satisfy liquidity constraint shown in the second equation. At the end of the intraday period, the agent receives payments from others, which we denoted by RT, and the available liquidity evolves as shown in the third equation. There is a cost associated with the delayed payment in each period. It is denoted by RD and shown in the fourth equation. The delay cost could represent customer dissatisfaction due to timely processing of their payments request during the day. Finally, let's move on to the end of the day settlement. The end of the day procedure is outlined in schematic shown in the right. In this period, each bank has to satisfy its payment demand for that day. In our setting, if the bank does not have sufficient liquidity to satisfy its payment demand, it must borrow additional liquidity from the central bank. The end of day shortage is shown in the second equation. The cost of end of day borrowing is greater than the initial liquidity cost. Therefore, for given day, which is same as one episode, the total cost is sum of initial liquidity per period delay cost and the borrowing cost. Therefore, in order to reduce the total cost, each bank has to strategically make liquidity allocation at the start of the day. In our paper, we use reinforcement learning to learn the initial liquidity decision in this simplified setting.
Thanks, Ajit. Hello, everyone. My name is Pablo Samuel. I work at Google, and I will be presenting the reinforcement learning component of this project. In reinforcement learning, we have an agent that interacts with an environment via making a set of action choices. Every time an action is made, the environment will return the next state that the agent just transitioned to, as well as a numerical signal in the form of a reward or a cost. The agent then incorporates these signals, the next state and the reward or cost, in order to learn how to act more optimally. In the context of our current project, we have two agents learning concurrently. Each of these agents represents one of the banks that Ajit mentioned in the previous slides. And at each action choice, each agent is deciding the initial liquidity or the payments to send at each time period. The environment then will return the cost for each of the agents, and each of these agents will independently learn how to minimize its cost. In reinforcement learning, we're typically dealing with behavior policies that we typically denote as pi, which are mappings from states to distributions over actions. And we can measure for each state what the value of a particular policy is. So if an agent is a state S, we denote the value of that state S under policy pi as V pi. And V pi can be defined via this recurrence, which is known as the Bellman recurrence. What it's doing is it has two main components. The first one is the cost incurred by the particular action choice, and this action A is sampled from the current policy pi. And the second component is the expected sum of discounted next state values. So to unpack this a little bit, we sample S prime from our transition dynamics P, and then we look at the value of that next state S prime under the particular policy pi, and we multiply this by a discount factor gamma. This is meant to encourage minimizing costs in the short term and not waiting too long to receive rewards or minimize cost. Ultimately, the agent is trying to find the optimal policy pi star, which is the argmax of this value function v pi. The algorithm we use for our particular project is a very old one that's been around for a long time called reinforce. And what it involves is given a start state S0 and a policy parameterized by some parameters theta. So what this means is that we can use, for instance, a neural network with parameters theta to represent our policy. We can then define the function j of theta as simply representing the value function for the particular policy pi parameterized at theta from the start state S0. So under this paradigm, we can update the parameters theta using stochastic gradient descent if we know the gradient of j. Now, this might not be so easy to compute, but thanks to the well-known policy gradient theorem, we can express the gradient of j in this closed form below. And this is using trajectories tau that are sampled using the policy pi. So tau is simply a collection of state action pairs done in sequence up to a particular horizon t. Now, using this policy gradient theorem, we can then sample trajectories, compute the gradient estimate, and apply stochastic gradient descent to improve the policy parameters so as to minimize the cost for each of the agents independently.
Hi, I'm Han from the Bank of Canada, and I will walk us through our learning setup and our results. Our reinforcement learning agents were tested on two distinct experiments. In our first scenario, we construct an arbitrary configuration of two periods of payment demands. Since we know the analytical solution for the two-period problem, the agent's success supports our use of the reinforcement learning algorithm. In the next scenario, we use aggregated real data from Canada's high-value payment system to construct an instance of the problem with 12 periods of payment demands. In both experiments, our state space is represented as the vector of payment demands per period. Our action space is represented by a fraction of available collateral, the amount the agent sends to other participants in the system. We discretized our action space into 20 actions. The cost function is represented by the addition of the cost of collateral pledged to the system, the sum of delay cost per period, and finally, the borrowing cost for any liquidity shortfall at the end of the day. We chose a configuration of the relative costs that impose a realistic relationship observed in the actual payment system. To observe robustness, we run our experiments 50 times independently so we can determine the stability of solutions given by our reinforcement learning algorithm. In this specific instance of the two-period problem, we can see that agent A does not have a payment in the first period, and agent A's second period demand can be fulfilled by the entirety of agent B's first period payment demand. With this special example, we can easily calculate optimal choices. That agent A's optimal liquidity choice is 0, and agent B's optimal liquidity choice is 0.2. The solid blue and orange lines in the graphs represent the average costs and decisions made at each learning episode across the 50 independent trials. The band represents the 99% confidence interval. The dotted line is the optimal cost and decision in each case derived from the analytical solution. The plots show us that our reinforcement learning agents were able to learn to allocate liquidity exactly as expected, giving us final optimal costs of 0 for agent A and 0.02 for agent B. For the richer 12-period problem, we use real data from Canada's Large Value Transfer System, the LVTS, normalized by their available collateral. We aggregated the payments observed between two LVTS participants in hourly intervals. The data contains 380 business days worth of payments between January 2018 and the end of August 2019. One remarkable note to make here is the difference in average cumulative payment demands for each bank, suggesting that agent A tends to receive more payments than agent B. We can observe that the learning process is more gradual as we increase the complexity of the problem. With increased complexity, we also see that the learning process is noisier than the simpler two-period problem. Note that there is no analytical solution for this scenario. However, we did a separate brute force search to verify that our agents' ending choices were within the range of the expected result that minimizes the costs in the system as a whole. When studying different cost configurations of the system, we also found that the profile of payment demands matter. Agent B is more sensitive to a change in the delay cost since it serves higher payment demands, making it more likely to be a liquidity provider than a liquidity receiver.
Thank you, Han. I'm Rod Garrett from the University of California, Santa Barbara, and I'm going to provide some concluding remarks. As we showed in this presentation, in the two-period setting, our RL agents demonstrate optimal learning behavior in the initial liquidity choice problem. In multiple period settings, it's hard to verify if agents learn the optimal behavior, but generally we find that total cost decreases as training progresses. The initial liquidity problem that we analyze is an important one, but it is not the only decision that payment processors at banks have to make. They also have to decide how to allocate available liquidity intraday. In our framework, this decision is trivial because delaying payments is costly and payments are divisible. Hence, agents should complete the largest possible share of their required payments, given available liquidity at any point during the day. We demonstrate in an appendix of the paper that if we give banks an exogenous amount of initial liquidity, the RL agent can learn the simple rule. Liquidity decisions of banks are complex even when agents have full knowledge of the environment and the data generating process. Our agents learned optimal behavior despite having no knowledge of the environment, the data, or the game. The results suggest that there is potential for regulators to use RL policies to help in their mandates of ensuring safe and efficient payment systems. In order for the full potential of this work to be realized, we plan to modify the problem so that agents learn a single policy function for multiple tasks, and we intend to add more realistic features of large value payments. Of particular interest is the introduction of indivisible and urgent payments, as this creates a strategic incentive for intraday delay that is missing in the current analysis. We also hope to eventually model an intraday market for liquidity and extend the analysis to N agents. Thank you for watching this presentation.